Ever wondered how transformers, the models behind ChatGPT and BERT, can be used for image classification? In this video, we're diving deep into vision transformers, or ViTs, and we'll build one from scratch, using a simple dataset, MNIST. Transformers were originally built for sequence data, like text. But researchers quickly realized that images can be broken into sequences too. That's the idea behind vision transformers, first introduced by Dosovitsky et al. In 2020. Today, we'll learn how ViTs work by applying them to the MNIST dataset, a collection of handwritten digits, each in a tiny 28 by 28 grayscale image. It's simple, perfect for learning. Unlike CNNs, ViTs don't scan an image pixel by pixel. Instead, they divide an image into smaller fixed-size patches. For MNIST, we split each 28 by 28 image into 7 by 7 patches, each 4 by 4 pixels. We then flatten each patch and turn it into a vector, giving us a sequence of 49 tokens, just like 49 words in a sentence. Next, each patch vector is passed through a linear layer, a simple neural network layer, to project it into a new space, say, 8 dimensions. But we're missing one crucial thing, the order. Unlike CNNs, transformers don't understand position. That's where positional encoding comes in. We add a unique pattern to each patch vector to encode its position in the image, high frequency for early positions, low frequency for later ones. Now comes a neat trick. We add a special token, called the classification token, that learns to represent the entire image. After processing through the network, we'll use this token alone to classify the digit. Pretty cool, right? Now that we've patchified the image and prepared our token sequence, it's time to look under the hood of what actually powers the vision transformer, the transformer architecture itself. At the heart of ViTs is the transformer encoder, the same architecture used in models like BERT. Let's break it down. Embedding layer. In ViT, each image patch is linearly embedded into a vector. This is like token embeddings in BERT. Positional encoding. Since transformers don't understand order, we add a fixed positional vector to each patch token, just like in NLP models. Encoder stack. This is where the magic happens. Each encoder block contains 2 main parts. Multi-head self-attention. Feed-forward neural network. Let's zoom in on the multi-head self-attention layer, the real engine of the transformer. Here's how it works. Each patch token generates 3 vectors, a query, a key, and a value. We calculate how much attention one patch should pay to another by computing the dot product between queries and keys. These scores are then scaled, optionally masked, and passed through a softmax function to generate attention weights. Finally, these weights are applied to the value vectors to get a new context-aware representation of each patch. These are called context vectors. This process is done in parallel across multiple heads, each learning a different type of relationship. Next, the output of attention goes through a feed-forward neural network, a small MLP that processes each token individually. And throughout all of this, residual connections and layer normalization help stabilize training and speed up learning. After passing through several of these encoder blocks, our class token has gathered information from the entire image. We feed it into a final MLP layer to produce our prediction, a digit from 0 to 9. And that's it. Our vision transformer is now ready to classify handwritten digits. Let's start with the imports then. Let's create a main function that prepares the MNIST dataset, instantiates a model, and trains it for 5 epochs. After that, the loss and accuracy are measured on the test set. Now that we have this template, from now on, we can just focus on the model, ViT, that will have to classify the images with shape, nx1 by 28 by 28. Let's start by defining an empty NN module. We will then fill this class step by step. Forward pass. As PyTorch, as well as most DL frameworks, provides auto-grad computations, we are only concerned with implementing the forward pass of the ViT model. Since we have defined the optimizer of the model already, the framework will take care of back-propagating gradients and training the model's parameters. Let's look at this image from ViT. In the picture, we see that the input image, A, is cut into subimages equally sized. Each such subimage goes through a linear embedding. From then on, each subimage is just a one-dimensional vector. A positional embedding is then added to these vectors' tokens. The positional embedding allows the network to know where each subimage is positioned originally in the image. Without this information, the network would not be able to know where each such image would be placed, leading to potentially wrong predictions. These tokens are then passed, together with a special classification token, to the transformer encoder's blocks, where each is composed of a layer normalization, LN, followed by a multi-head self-attention, MSA, and a residual connection. Then a second LN, a multilayer perceptron, MLP, and again a residual connection. These blocks are connected back to back. Finally, a classification MLP block is used for the final classification only on the special classification token, which by the end of this process has global information about the picture. Let's build the ViT in 6 main steps. Step 1. Patchifying and the linear mapping. The transformer encoder was developed with sequence data in mind, such as English sentences. However, an image is not a sequence. It is just, an image. So how do we sequencify an image? We break it into multiple subimages and map each subimage to a vector. We do so by simply reshaping our input, which has size n, c, h, w. In our example, n, 1, 28, 28, to size n, #patches, patch dimensionality, where the dimensionality of a patch is adjusted accordingly. In this example, we break each 1, 28, 28 into 7 by 7 patches, hence, each of size 4 by 4. That is, we are going to obtain 7 times 7 is equal to 49 subimages out of a single image. Thus, we reshape input n, 1, 28, 28 to n, p superscript 2, hwc / p superscript 2 equals n, 7 by 7, 4 by 4 equals n, 49, 16. Notice that, while each patch is a picture of size 1 by 4 by 4, we flatten it to a 16-dimensional vector. Also, in this case, we only had a single color channel. If we had multiple color channels, those would also have been flattened into the vector. We modify our myViT class to implement the patchifying only. We create a method that does the operation from scratch. Notice that this is an inefficient way to carry out the operation, but the code is intuitive for learning about the core concept. The class constructor now lets the class know the size of our input images, number of channels, height, and width. Note that in this implementation, the n_patches variable is the number of patches that we will find both in width and height. In our case, it's 7 because we break the image into 7 by 7 patches. Now that we have our flattened patches, we can map each of them through a linear mapping. While each patch was a 4 times 4 is equal to 16-dimensional vector, the linear mapping can map to any arbitrary vector size. Thus, we add a parameter to our class constructor called hidden_d for hidden dimension. In this example, we will use a hidden dimension of 8, but in principle, any number can be put here. We will thus be mapping each 16-dimensional patch to an 8-dimensional patch. We simply create a NN, linear layer, and call it in our forward function. Notice that we run n, 49, 16, tensor through a 16, 8, linear mapper or matrix. The linear operation only happens on the last dimension. Step 2. Adding the classification token. If you look closely at the architecture picture, you will notice that also a v_class token is passed to the transformer encoder. What's this? Simply put, this is a special token that we add to our model that has the role of capturing information about the other tokens. This will happen with the MSA block later on. When information about all other tokens will be present here, we will be able to classify the image using only this special token. The initial value of the special token, the one fed to the transformer encoder, is a parameter of the model that needs to be learned. This is a cool concept of transformers. If we wanted to do another downstream task, we would just need to add another special token for the other downstream task. For example, classifying a digit as higher than 5 or lower, and a classifier that takes as input this new token. Clever, right? We can now add a parameter to our model and convert our N49,8 tokens tensor to an N58 tensor. We add the special token to each sequence. Notice that the classification token is put as the first token of each sequence. This will be important to keep in mind when we will then retrieve the classification token to feed to the final MLP. Step 3. Positional encoding. As anticipated, positional encoding allows the model to understand where each patch would be placed in the original image. While it is theoretically possible to learn such positional embeddings, previous work by Vaswani et al. Suggests that we can just add sines and cosines waves. In particular, positional encoding adds high-frequency values to the first dimensions and low-frequency values to the latter dimensions. In each sequence, for token I we add to its JTH coordinate the following value. This positional embedding is a function of the number of elements in the sequence and the dimensionality of each element. Thus, it is always a two-dimensional tensor or rectangle. Here's a simple function that, given the number of tokens and the dimensionality of each of them, outputs a matrix where each coordinate, ij, is the value to be added to token I in dimension j. From the heat map we have plotted, we see that all horizontal lines are all different from each other, and thus samples can be distinguished. We can now add this positional encoding to our model after the linear mapping and the addition of the class token. We define the positional embedding to be a parameter of our model that we won't update by setting its requires_grad to false. Note that in the forward method, since tokens have size N58, we have to repeat the 58 positional encoding matrix n times. Step 4. The encoder block. Since quite some computations are carried out, it is worth creating a new class for MSA. Notice that, for each head, we create distinct Q, K, and V mapping functions, square matrices of size 4 by 4 in our example. Since our inputs will be sequences of size N58, and we only use 2 heads, we will at some point have an N52, 4 tensor, use a NN linear 4 module on it, and then come back, after concatenation, to an N58 tensor. Also notice that using loops is not the most efficient way to compute the multi-head self-attention, but it makes the code much clearer for learning. We will add a residual connection that will add our original N58 tensor to the N58 obtained after ln and MSA. It's time to create the transformer encoder block class, which will be a component of the ViT class. Phew, that was quite some work. But I promise this was the hardest part. From now on, it's all downhill. With this self-attention mechanism, the class token, first token of each of the n sequences, now has information regarding all other tokens. All that is left to the transformer encoder is just a simple residual connection between what we already have and what we get after passing the current tensor through another ln and an MLP. The MLP is composed of 2 layers, where the hidden layer typically is 4 times as big. This is a parameter. Now that the encoder block is ready, we just need to insert it in our bigger ViT model, which is responsible for patchifying before the transformer blocks and carrying out the classification after. We could have an arbitrary number of transformer blocks. In this example, to keep it simple, I will use only 2. We also add a parameter to know how many heads does each encoder block will use. Once more, if we run a random 7, 1, 28, 28 tensor through our model, we still get a 7, 50, 8, tensor. Finally, we can extract just the classification token, first token, out of our n sequences and use each token to get n classifications. Since we decided that each token is an 8-dimensional vector, and since we have 10 possible digits, we can implement the classification MLP as a simple 8 by 10 matrix activated with the softmax function. The output of our model is now an n10 tensor. Hooray, we are done! We changed the only line in the main program that was previously undefined. We now just need to run the training and test loops and see how our model performs. If you've set torch seed manually to 0, you should get this printed. And that's it. We have now created a ViT from scratch. Our model achieves 80% accuracy in just 5 epochs and with few parameters. Pretty amazing for such a minimal model.